Good afternoon, everybody. I'm going to give a lecture today on the expanding universe and tell you a bit about this rather, it still seems a bit bizarre to think that everything, all the space around us is expanding, moving away. It's even bizarre to think that the surface under our feet is, spinning rapidly. We've gotten used to that. We accept that the Earth itself is moving around the sun. We've accepted that for a few hundred years, pretty much. But the fact that the whole universe, all the space is expanding, was something that really only was understood in the 20th century. So it's rather a recent idea. So let me tell you, I'm going to begin by telling you some of the historical characters involved in this story of how we came to realize that we live in an expanding universe. So here is perhaps the pioneer of everything in this field. Alexander Friedman is a Russian who was trained as a physicist and a mathematician and also worked as a meteorologist. And he was one of the few people who appreciated Einstein's theory of general relativity when it was first announced around 1916 or so. And at that time, Einstein had developed the idea of a model for the universe. And he realized that in his system, which explained gravity, that gravity tended to pull things together. And his model for the universe, all the space around us, the largest scales one could see, because of gravity would collapse. And Einstein was very unhappy with this. So he said, well, let me invent a hypothetical force, which was just a constant term in his equations, really, called the cosmological constant, which acted a bit like anti-gravity. And that way he got a static universe. And he was happy, but it was really an unfortunate way of doing physics, because he invented something which was no justification to develop his model for the universe, whereas all the rest of his theory of relativity, that there were tests, there were experiments one could do to prove it. But for this particular thing, at that time, there was no conceivable test. It was just a mathematical assumption to make his equations resemble the universe which his prejudice led him to believe was static. Okay, so along comes Alexander Friedman. He realizes that Einstein had made a simple mathematical mistake when he was working out his model for the universe. He somehow divided both sides of the equation by 0 in one of the derivations, and so he missed a very, very important possibility. And this was that gravity allowed the possibility of a universe to be expanding. Okay, if it was expanding, then there was no need to invent any weird bit of physics to stop it from expanding or make it static or whatever. And so Friedman published in 1922 his solutions for the expanding universe. And Einstein, at first, didn't believe it. He'd heard about it. He saw the paper in German, written in German originally, actually. And he said, this can't be right. And then there was correspondence between the two. And eventually, Einstein conceded that Friedman might have a good point that Einstein had missed. And that, okay, fine. But it was just some bizarre, weird thing for Einstein to put in the corner of, possibilities. He didn't take it seriously. Okay, so that was the story of Alexander Friedman and Einstein. Then along comes someone else, okay? And so Georges Lemaitre was ordained as a Jesuit priest, in fact. He was obsessed by physics and by general relativity too. There were very few people who understood Einstein's theory, and Lemaitre was one of the few at the time. And he went to work first in England as a young man to begin to get his PhD, And then he went on to MIT, and he got a doctorate on solutions in general relativity, possible. Nothing to do with cosmology. Then he went out to Pasadena to meet some of the astronomers, and he began to learn astronomy, and he also, totally independently of Friedman, worked out that there should be an expanding universe, that it was very much a possibility. And what Lemaitre knew about that Friedman did not was that there was an American astronomer working in Flagstaff, Arizona, called Vesto Slipher, and he, for decades, from the early years of the 20th century, had been measuring these weird redshifts in nearby galaxies, that is, velocities of movement away from us, apparent velocities of movement away from us. And Slipher hadn't the slightest idea what this meant. He just recorded the data. And when Lemaitre got to see the data after talking to other astronomers, he realized that what this meant was that the further away a galaxy seemed to be, and the distances were rather crude at the time, the faster it seemed to be moving. And Lemaitre said, this is exactly what my theory of expanding space leads me to believe. And he went on to publish his work. Unfortunately, he published it in French, in a Belgian journal that was not read by anyone probably outside of Belgium or France. And so the news did not get to the Americans who had the big telescopes at the time. And so here is an interesting quote from Lemaitre later on. The evolution of the world can be compared to a display of fireworks that has just ended. This is very timely. Guy Fawkes Day is coming up. Some few real wisps, ashes and red wisps, ashes and smoke, standing on a cooled cinder. We see the slow fading of the suns. We try to recall the vanished brilliance of the origin of the world. So he wrote that in a later popular book. Well, back to California. So 2 years after Lemaitre published his ideas in French, which had no significance whatsoever for the observers, they didn't know about it at the time, Hubble, who was one of the leading American observers, working at Mount Wilson, 100-inch telescope, so he was able to take Slipher's galaxies with the redshifts measured by Slipher, and Hubble had the brilliance of being able to figure out ways to get the distances, more precisely than anyone done before. And so he realized that, again, the universe was possibly expanding, except that Hubble, bizarrely, could never quite accept the fact that redshift meant velocity. I mean, it was disputed at the time, actually. There were bizarre models of relativity which showed that you could imagine a universe with redshifts of galaxies without expansion. Bizarre things that no one really understood at the time. So Hubble was a bit dubious about making the universe expand, because if it expanded according to Hubble, it would have to be rather young, right? You could figure out from the rate at which it's moving apart that it had a certain age. And at that time, it was rather strange. He measured, because of observational uncertainties and errors at the time, rather a young age for the universe. He said it would be suspiciously young, and at the beginning, curiously small and dense. And then, if redshifts are not Doppler effects, these anomalies disappear. And so he, even in 1937, didn't quite believe in expansion. Anyway, but in 1929, he published his results on the relation between the Doppler shift and the distance. And that was the first real breakthrough in modern cosmology, because this essentially, if we take the conventional understanding of red shifts, Doppler shifts, this was the expanding universe, the beginning of the expanding space being expanding. So Einstein enters the story, and he was this real skeptic. Like all his contemporaries at the time, the universe had to be static. It didn't make sense to have an expanding universe. And it was only when, in 1930-31, he went to visit Hubble, and in this, I assume, staged photograph, you have Hubble letting Einstein look through the telescope and verify for himself that the universe was expanding. And then a year or two later, eventually, Lemaitre's ideas were translated into English, and they got through as well. And you see here Lemaitre and Einstein. This was taken in 1931 in in Pasadena having a conversation, and Einstein at that point was totally convinced that we lived in an expanding universe. And here you see Lemaitre some years later lecturing on the subject. So he was one of the great modern cosmologists, and it's interesting to reflect on this because here we have someone who's basically, an ordained priest, and he later rose to a very high position as a scientific advisor to a pope whose picture I'll show you in a second, and yet he was totally happy with this notion of what came to be called the Big Bang, the creation of the universe, in fact, some tens of billions of years ago. And here, for example, you see Lemaitre when he became advisor to Pope Pius XII, who incidentally was the Pope during the Second World War, and there are many stories about his relations with the Germans and so forth. But anyway, he was certainly, as far as science goes, very much sympathetic to Lemaitre's views about the Big Bang Theory and the fact that the universe was tens of billions of years old. Now, why was this such an interesting question to discuss with the Pope at the time? Well, here is the reason. If you go back to St. James' version of the Bible, you can actually, what was done by Bishop Ussher in the 19th century, you can retrace the age of the universe because it tells you, so-and-so begat so-and-so, begat so-and-so, etc., etc. You all read all this in the Old Testament. And if you assume a certain time for the begatting, etc., each generation, you figure out how many generations there were. And lo and behold, what Bishop Ussher found was that from this interpretation of the St. James version of the Bible, on Sunday, October 23rd, 4004 BC, that was the creation of the universe. That was the first day of creation. Okay, so interesting, and there are, of course, many people that believe in this. I'm not quite sure what the ratio is in the UK, but in the US, this poll some years ago found that half of the population there believed in creationism, which is the name of this literal interpretation. In the UK, I think people are possibly more skeptical. This was another poll I found somewhere that Britons believe more in ghosts than in God, but that's another story. Anyway, but it's interesting to think of this in the context of the Catholic Church, actually, this discussion, because there is a very centralized leadership, and so one can sort of have a more coherent view of the relation between religion and science and the Big Bang and evolution. And so this was one discussion some years ago by Pope John Paul. No conflict with the theory of evolution. This has had its ups and downs, actually, in recent years in the Catholic Church. There was a succeeding post that was somewhat anti-evolution, but the latest one seems very positive. The theories of evolution, the Big Bang, are real, and God is not a magician with a magic wand. So Pope Francis declared a couple of years ago. This, as far as the Church anyway, put an end to the pseudo theories of creation and intelligent design from that corner. Okay, anyway, so let me now move away from the interface of the Big Bang Theory, I'll tell you in a moment why it's called the Big Bang Theory, and theology, and go back to physics. So, in the 20th century then, in the 1930s basically, there were many ideas about the expanding universe, whether it would expand forever or reach a maximum size, then start contracting, or just keep on going very more and more slowly forever. All this was debated, but what was totally clear to everybody was that this theory predicted there was a very dense beginning a long time ago, okay, and how long ago depended on how accurately you could measure the rate of expansion of the universe, which we'll come to in a second. Okay, but this fact that the universe was once very dense and most likely very hot made it an interesting place to explore ideas about physics. Now, the astronomers at the time didn't know much about about nuclear physics. They were not even, it took a while for them to even appreciate that the sun shines because of nuclear reactions in the center. And this understanding came about because the nuclear physics community realized that astrophysics and cosmology was somewhere where they could test many of their theories of how nuclei work. And the Big Bang provided a beautiful demonstration, in fact, of how this worked. There was one young man called George Gamow who worked as a physicist in Russia at the time, and he, as the regime there got more and more oppressive in the 1920s, he tried very hard to leave, and finally in 1932 he did manage to leave and eventually moved to the US. And in the US he had a professorship at George Mason University, and there he applied his ideas about cosmology. He said, well, the fact the universe was so hot at the first few minutes meant that the nuclei which were there, the protons and the neutrons, would be combined together, and they would, a helium atom is a mixture of 2 protons and 2 neutrons, so they would fuse together if you have high enough temperatures and make helium. And the helium, he thought, could fuse together again at high enough temperatures and make carbon, for example. That's 3 by 3 helium nuclei. And as you, and if you have enough energy present, you can do this. Now, so he launched this wonderful idea, really, along with his graduate student and a colleague of his. And they said that in the first half hour of the Big Bang, they thought that all of the elements that we're made of could be created. That was their idea. It was a wonderful place for doing nuclear physics and making us, basically, the elements of which we're made. However, they made one mistake, okay, which they realized eventually. This is around 1950. And the mistake was that they could make helium, okay, out of hydrogen. That's wonderful because helium is the second most common element in the universe. Something like 30% of the mass of the universe is helium. So that's already a great start. Now, helium is made in stars. Stars like the sun are turning hydrogen into helium a little bit, okay? But that's where the energy comes from in a star. That's where hydrogen bombs get their energy too. But not nearly enough to give you the 30% that we see in the universe. So it came from before the first stars. And the Big Bang, the beginning, is the obvious place. But the mistake Gamow made was that helium has atomic mass 4, and to make carbon, which is another very common element, you have to take 3 helium. You go from 4 plus 4 is 8, and then up to 12, 2 at a time. Unfortunately, there is no stable element of mass 8. Beryllium is an unstable isotope of mass 8. It's mostly mass 7, which means that it's like climbing a ladder and your second rung is broken, so you can't get to the third rung. And so the way so you make helium, but you don't do much better, okay? But that's already wonderful. How do you make the stuff that we're made of? Well, you have to somehow get 3 bits of helium to come together. And that's called a 3-body reaction. And the place that can happen is inside a star, because inside a star, you have the same conditions you had at the beginning of the universe. It's a very hot, dense state, but the star's not expanding rapidly. It's staying there for a while, and that gives you time to build up the carbon and everything else for that matter too. And then eventually the star dies, it explodes, and then those elements are ejected and mixed in with everything else, and that's where we are today. And so here you have the pioneers of how stars make the heavy elements, another vital part of our story. Geoffrey and Margaret Burbidge, 2 English astronomers who moved to California for most of their careers, Fred Hoyle on the right. And these 3 were rather unconventional astronomers because they did many other things. They never really were what one might call mainstream cosmologists. whereas William Fowler was a nuclear physicist who was absolutely devoted to understanding the heavy elements. And so when it time to give out the Nobel Prize for this work, it was Fowler, as it happens, that got the prize and not the others, but I think they all would have deserved it. And here you have the story that these four developed, which is that as stars age, the centers get hotter as they contract, and they make heavier and heavier elements. Eventually, the center of a star fuses into iron, and iron is what you might call the ultimate slag heap of the universe. You can't get any more energy out of iron, that's it. And so then the star will explode, okay? And then from this exploding star, you then get the silicon and the magnesium and everything else, the carbon that we're made of. So that was the way the story of the universe can now explain all the stuff that we made of, the elements, the chemistry that we made of. That does come out of a mixture of the first minutes of the universe and stars that explode. So moving on, this was in the 1950s, this development. In the 1960s, there was another indispensable part of the expanding universe theory, which is that astronomers realized that most of the universe, which makes up the expanding universe, is actually invisible. It's dark. This is a wonderful story in itself, and it was the charge was led actually much earlier by an astronomer called Fritz Zwicky, who was Swiss originally, and then again went to California for most of his life. And he had a very low opinion of his colleagues, and you see him making this gesture on the right, which, people have one interpretation is calling somebody a spherical bastard, okay? It doesn't matter which direction you look at him, is right, whatever. Okay, anyway, he was the person who studied galaxy clusters, I'll show you those in a second, and realized that they were a great source of dark matter. But before we come to that, let me tell you about the 1960s contribution, which was pretty much the hardest proof, really, that we have lots of dark matter. So Vera Rubin measured galaxies. This galaxy is the one large galaxy you actually just see with the naked eye as a fuzzy patch near the square of Pegasus on a very dark night. Andromeda Galaxy, or Messier 31. And she measured stars, the motions of stars from their spectra, and found that as you moved away from the center, the motions didn't go down. They stayed sort of constant. Even though all the light is going down, you see, as you get to the outer part, there's less and less light. But the velocities, the orbital speeds of the stars stay about the same. Very, very strange. This meant that something is pulling them, and that something is not the luminous stuff, it must be something dark. And so when you just look at optical stuff, you can't get out very, very far. And the vital addition to what she did was by a radio astronomer who used the radio lines of hydrogen to measure gas clouds. And he found the same thing, went way, way out, total darkness, yet something is causing these stars to orbit around the galaxy. Otherwise, they'd be flying apart. And so that really is the story of dark matter. This is the sort of radio telescope that Roberts used at Greenback, 300 feet in diameter. And so our current view then is that we observe these velocities. If you had only the stars, you'd get much smaller speeds, and the dark matter is needed to explain all of that. And this story has been amply verified with modern data. You can see these are many different galaxies, and all of them invariably, basically, the motions of the stars stay about the same the further out you go. So going back to Fritz Zwicky, this was around in the early 1950s. But the amazing thing about Zwicky is that he wrote this paper in 1933. And he realized that das dunkle Materien, dark matter, is basically abundant in galaxy clusters. These are groupings of galaxies, thousands of galaxies. Here's a picture of of one of the galaxies studied. This is the Coma cluster on the left. And he realized that at that time, they'd measured velocities of the galaxies, and they'd be flying apart if there was not a lot of 10 times more dark matter than he saw in ordinary light, which is what he wrote in his paper. What is interesting is that we now have a totally modern view using Einstein's prediction that gravity bends light rays. Okay, this was space is curved, so Einstein told us that was the new way of understanding gravity. And this means that when you look at a system containing lots of dark matter, you should see weird effects on the background galaxies, because the light from them passing through the cluster of galaxies, which is mostly empty space, lots of space between them, the light from the distant galaxies gets slightly twisted, slightly curved. And so this map on the right is a map of what we call gravitational shear, a map of the dark matter. And that really vindicates a major prediction of Einstein from the 1916 or thereabouts, but also vindicates Zwicky's idea that this cluster is full of dark matter. Okay, so here's another weird thing about the dark matter. Okay, so here is a modern observation taken with the X-ray telescopes and big optical telescopes of a galaxy cluster called the Bullock Galaxy Cluster. And you see it looks a bit weird. What you see in the red is the X-ray image. So it's the gas in the cluster, okay? And basically the cluster is full of hot gas, and galaxies too. We just look at the galaxies. But from the hot gas, from its temperature, you can figure out the gravity and everything else. So this is where the cluster is. But most of the mass, which you now study from the distortions of the background galaxies measuring each image, they're slightly shifted, slightly bent, and then you put everything together, you make a map, and the blue light there is this map. And you can see this was a pair of clusters that were merging together. Things tend to do that in the universe. And the gas has come together not nicely, but the dark matter, it's gone through like a ghost in the night, right? And it's come out the other side again, which tells us that the dark matter is something that interacts really, really weakly with ordinary matter, which is partly why we haven't seen it yet, and partly why it's in the outer parts of galaxies. It hasn't fallen to the middle. So that is the way now you can see the latest telescopes and optical X-ray are now adding together to get us closer to piecing this puzzle, dark matter's weak interacting. Okay, so that now gets us onto the Big Bang, which is the culmination of our understanding of the expansion of space, the expanding universe. And the modern mid-20th century piece of information that added to that and is now one of the most vital parts about the whole story was the discovery of the cosmic background radiation by these two gentlemen, radio astronomers who were actually looking for mapping the Milky Way and found this rather bizarre signal from all over the sky that they realized eventually after they were unaware of Gamov's ideas about a hot early beginning to the universe. Gamov even predicted the universe should expand and have some temperature today. Well, they were unaware of this prediction, but they discovered this microwave radiation coming all over space, which is the fossil radiation from the first minutes of the universe. And modern observations, again, they made their discovery in 1964. They measured at one frequency, but 26 years later, a satellite filled in all the details, all the spectral points, the frequency points. And this is what we call a spectrum, showing you that this background radiation is perfect black body radiation, which means that the early universe was like a perfect oven, expanded, and the radiation is the fossil relic of what was left behind. Its temperature today is just 3 degrees of absolute zero, microwaves. But once upon a time, it was billions and billions of degrees in the first few minutes, and that was hot enough to cook the elements and all that stuff. This is what's left over. Okay, so I was rather lucky in my career. I began as a graduate student roughly at this time when all this is being discovered. Okay, and so it's always very good to be in a new field that's just beginning, because it's like picking the low-hanging fruit on trees, basically. After a while, when you get far more details, it gets more difficult. But nevertheless, it was not always easy. So here is one letter to me from the president's office at my university at Berkeley, when I was in those early days, addressed to me in the Department of Astrology. So they, it took a while, for all of this to... Astrologers are still paid far more than astronomers, I'm sure, but that's another story. Okay. Anyway, so it wasn't measuring this radiation was one thing, but what you ideally want to do was to, it was realized that this radiation had to have variations from place to place on the sky. And the reason for that is that, we have a universe that's highly structured. It's full of galaxies and stars and people, whatever. But this meant that they must have formed from some sort of seed fluctuation. So when you look at this background radiation, there should be, little bits that are hotter, colder, whatever, that eventually, as gravity could operate, fell together and made structures. And so it's like doing archaeology in the sky. You want to look for the seeds from which we began. And the reason it was so difficult was that one is looking through this very, very murky galaxy that we live in, and our detectors are noisy and so forth. And way on the left over there is this elusive signal you might be looking for, slight variations in this microwave background. And it wasn't easy, and this figure on the left shows you how when they first observed the radiation, the microwaves, the theory told them they now had to go and look for tiny variations, but over the years, it was nearly 30 years actually, the theory did improve, and so that they made it harder. There was like a moving target, and the observations got better. And it was only around 1990 that they met success. Okay, and so in 1992, I guess, was when the paper was published. The first measurements of the variations in the temperature of this microwave background that filled the sky, the relic from the early universe. So here is the sort of story that you might see. So why was it so hard to see? Well, on the left, this is an example. On the left, you see a picture that you recognize, the Earth, right? And now imagine taking this picture, looking at it through the eyes of this satellite, this COBE satellite, and putting in all the noise, all this murky stuff that's stopping you from seeing the signal, and you get the picture on the right, okay? So that's how the Earth would look as viewed by this COBE satellite, the one that discovered the fluctuation the first time. So clearly, it's not obvious, right? But buried inside there, if you work on this a bit, you come up with this picture which made the headlines in 1992, where you see the red stripe in the middle is the Milky Way, which is taken away, and above and below you see these first indications of rather gigantic scale fluctuations a few degrees across. So that was the Washington Post, and in the UK, we still had the Independent in those days. And this was, the front page, how the universe began, the holy grail of cosmology. So it created lots of interest, even in the French newspapers. This is sort of on page 3 of Le Monde, I think, at the time. Le grumeau de la soupe cosmique. Means the ripples in the cosmic soup. Okay, so that was all very wonderful. And things have gotten better since. Okay, so that was in 1992, and then we flash forward to 2006. Another satellite, the next one, devoted to looking at the microwave sky, came up with this map. And you can see now we really are looking with decent angular resolution. The top map was just a broad brush structure. You can maybe see the continents on that structure, but you can't see the mountains and the valleys. On this, you can now see the mountains and the valleys, which are where all the true interesting things lie, because we're trying to understand how those mountains and valleys form. Of course, forming the continents is a great thing too, but it's the mountains and valleys where we live, basically. Okay, and this discovery got these two gentlemen the Nobel Prize a few years later, George Smoot and John Mather. Well, not everyone was happy with this notion of the expanding universe. So here are 3 famous heretics. So these were the founders of the steady state universe. And so Fred Hoyle on the right, Herman Bondi in the middle, Tommy Gold on the left. And in 1951, Fred Hoyle gave a series of radio lectures on the BBC, and he invented the word the Big Bang in those lectures. So he was trying to be, he was being, sarcastic, really, saying this is such an impossible idea to think that everything began in a nanosecond or less. And so here's the view that he and his colleagues articulated was that, well, we can avoid all this if we can think of some way to replace the stuff that's moving away. And so in his view, you could imagine continuous creation of something out of nothing, okay? Now, in a way, our whole universe, in some sense, came out of nothing. That's another story. I'll come to that perhaps in a moment. But what he wanted to do was to argue that this happened today, okay? And so this then led him to the steady state universe. Things were created and made the stars and the galaxies out of nothing everywhere. And so he didn't need to have a hot and dense beginning. Everything, is always the same on the average. Okay, and so then, well, that theory survived for a while, but with the microwave background being discovered, that was definite proof of a hot beginning, and I showed you the beautiful black body radiation. And so that, plus other indications, meant this was a theory that had a success for a while and then died. Okay, and it's always good, in science to be able to falsify theories. You can rarely prove anything is right, but because there may always be some greater theory in the future, but you can at least falsify things, show the evidence shows things are wrong. And this I think we can, all my colleagues would agree we've done that for the steady state theory, which leaves us with the Big Bang theory. So I wrote a book on this, which still can be found, I guess. It's out of print, but it was translated. But you can tell, interestingly enough, the style of the front cover. This was the Russian translation, so a more sober version. And then, and the title was used by many others. So here's a book you may have read, a more recent one, by Simon Singh, also about the Big Bang. And the French are great at what they call bande dessinée, which are cartoon books. And so there's a wonderful cartoon book on the Big Bang too, which I strongly recommend. And back there you see an eminent French cosmologist, actually, the guy with the beard called Hubert Reeves. So why was it hard to accept the Big Bang? Well, the reason was that in the sky, we have one version of, the age of the universe. It's expanded, gave us a certain time from the rate at which it's expanding. Well, there's another totally independent way of getting ages, and for a long time, these two ages did not agree. And the Big Bang, as measured by Hubble, was simply too young to accommodate this age, which is the age you get from the Earth, by simply dating isotopes. Okay, so this is the way we do this. We go to an element like uranium-238, that's the isotopic mass, and you can measure its byproducts, right? And depending on the age of the rock, then the isotope ratios will be different. This is how we can date rocks, okay, of billions of years. Lead-205 is one of the major things that you measure. And so this basically is like an hourglass, you can see. So depending on how much lead-205 there is relative to other isotopes, you can figure out that it's a certain age. And we got ages of billions of years, which just simply did not agree with the smaller ages initially found by Hubble and his colleagues throughout the 1930s and 1940s. It was only really when there was a total blackout on Los Angeles in the Second World War that astronomer Walter Baade was able to, for the first time, actually get a more accurate distance to nearby galaxies and finally remove this discrepancy between the two ages. So going back to Lemaitre, this is a sketch from one of his notebooks, never published, but showing his thinking in 1927, basically. And so Lemaitre had all these possibilities for the expanding universe. The universe, according to him, could expand and then crunch, come to a crunch, or it could expand forever and even be accelerating slightly, or else just be expanding and just until it runs out of steam, but it just keeps on going forever. And these correspond to universes, as he realized, that if it comes to a crunch, will be finite, but expands forever, space would actually be infinite, according to Einstein's theory. So going back then to the observational state, why were things so complicated? So this is Hubble's original plot, okay, 1929. And you notice that these points are sort of all over the place. They represent individual galaxies with the redshifts measured by Slipher. Hubble got the distances. And velocities on upwards, distance on the right. And from the slope of that line, you get the rate of expansion, basically, whatever the distance. And so what about Lemaitre? Well, he did not publish this diagram, but he used the data in 1927 and it's been reconstructed from his notes. Why didn't he publish it? Because after Hubble's announcement, Eddington, famous astronomer, director of the Cambridge Observatory, realized at a meeting he held that there was this young Frenchman in the audience who came up to him and said, and actually he'd already studied under Eddington, they knew each other well, that, I've already done this. And so Eddington showed him his notes, his book, which was in French, his paper in French. And so Eddington had it translated. And then when Lemaitre got the proofs, he said, 1930, this bit about the expansion and the data, Hubble did all of that a year or two ago. I don't want to repeat what Hubble did. He was just a very modest person, Lemaitre. So anyway, it never actually got published. But I think these days we do credit him with essentially getting the same number as Hubble a couple of years before. And what's happened since then is this. So the tiny part of space that Hubble and Lemaitre studied is that circle on the left, okay? And this is essentially distance as we're now moving away. So all the modern data now is going, decades and decades further in distance. We're measuring the rate of expansion, not quite the slope, a little bit less fast than Hubble and Lemaitre imagined. That's just because we have much more accurate measures of distances, but it keeps on going all the way until we get to speeds of a fraction, 10% of the speed of light or something. And at the very end on the right, you can see there's a slight deviation. The curve is curving slightly upwards, which means that the universe is beginning to accelerate, and that's another story we'll come to later, but that's only affecting the recent universe. But at the beginning, this is the immense progress we've made since 1927, 1929, and 80 years of progress, basically, with bigger and bigger telescopes. Okay. So that's the story of cosmology as it was, observational cosmology as it is now. But there was one major development on the theory side, and it's interesting sociology to realize that just as in the 1950s, it was the nuclear physicists that made this huge contribution. They taught us how helium was made. They also taught us how the stars underwent fusion in the center to generate their energy. That came from the nuclear physicists. Well, in 1980, the particle physicists had their turn. They realized that, fine, we have, in the first minutes, it's like the center of a star, it's very hot, we can do nuclear physics, but let's imagine going back much, much earlier, okay? They said, well, then we can get so dense, so hot, we can duplicate the conditions in particle accelerators, like the one in CERN or Fermilab. And what is more, we can go back even earlier and duplicate accelerators that we couldn't even build. We couldn't imagine building, okay? So the energies that you can accede to in the early universe, CERN, for example, the Large Hadron Collider is about, 50 kilometers in diameter or something. But if you wanted to go to higher energy, you need bigger and bigger colliders, right? To access energies that correspond to the beginning of the universe, you'd have to go from here to the moon, basically. Which is impossible given any reasonable budget with magnets or whatever. But the early universe does it for you. And so here is the sort of way that that works. So LHC means, this is the energy scale to the right, LHC means the Large Hadron Collider. That's where we are today. But in the beginning, you can go all these many, many decades in energy. So we're talking about hundreds of GeV, that's the unit we measure energy in, And so these enormous powers, trillions and trillions and trillions higher energy can be achieved in the early universe. It's an experiment that was done a long time ago, okay? So we can't control it, but you can look for the products and the consequences, okay? So here is one consequence that was realized in the 1980s, that as you go back at the very beginning, there's a big question mark. We don't quite understand how to mix gravity into all of this, but there's a time when all the forces were equal to each other. It's been called the grand unification of everything, okay? And as the universe cools down, the forces sort of reach their normal levels, they separate, they adjust to our low energy universe now that we live in. Otherwise, it would all be fried if there were life there, it wouldn't exist. So we have to be cool enough for chemistry to work, etc. But early on that wasn't necessarily true, and we have the relics now. And it so happens that as the universe cooled down and these different phases of matter separated, think of ice and water, two phases of the same thing, H2O. As they separate, you release something called latent heat, energy. This is why fish can survive in frozen lakes in the water, okay? Well, the same thing can happen in the universe. And these gentlemen realized that there would be a moment of inflation. A fraction of a second after the Big Bang, all this energy from phase separation gave you a huge expansion. It's hard to explain, a bit of hand waving is involved. The Big Bang, believe me, it was very, very, very big. Or trying to describe the size of the Big Bang, we have Alan Guth and Andrew Lindy were the two proponents of this in 1981, who've had this idea, both particle physicists by training, who came to cosmology and realized this was the place they could really try to test their theory of the phase transitions of matter, how we arrive at where we are, how things are once unified at the beginning. That was their motivation. Okay, so here's a cartoon which tries to put this in perspective a bit. And the scale is more or less real, but I want you to notice the shape, okay? It's totally irregular, okay? That is how it was before. And why do things change? Well, this is why things change. You can imagine blowing up a wrinkled balloon. It just becomes incredibly smooth, right? And locally, the surface is totally flat, okay? And if you would try to draw a triangle on that surface, you'd find that locally, Euclid's theory, three angles adding up to 180 degrees, will be satisfied. If you try to draw a triangle on some curved surface, then you'd have a surprise. You wouldn't, and this is the way that surprise works. So Einstein's gravity, in fact, does curve space. And so a triangle is a triangle. If I have a space which is flat, this is on a sheet of paper, imagine. You have to think of this in 3 dimensions. It's not so easy, but this is a nice analogy. But if I, on the other hand, make space curved like a sphere, then you can see my 3 angles add up to more than 180. And if I do the opposite on a hyperbola, they can add up to less. And so in principle now, we can look at the universe and we can try to decide, inflation predicts the thing on the left. Everything should flatten out. Is that what we measure or not? Well, this idea did attract artists, and the most famous example is M.C. Escher. And so he did a series of engravings called Angels and Demons. He was fascinated by the geometry of curved space. And so these are wonderful engravings. And you can see that in this picture, this represents the universe in which you get distortions. And this would be equivalent to the universe which looks like that on a sphere, okay, on a spherical space. Things get distorted bigger as you go further away. And he also did this engraving in which you see the opposite effect, okay? Things get smaller and smaller. So I strongly recommend Escher as someone who beautifully bridges, notions of science in art. Okay, so going back then to the background, the macro background. This is the experiment that was done to prove the curvature of space, to measure it. So when you look at this radiation coming from all over, the fossil glow, it's totally uniform, okay? It's a first approximation. But buried inside that glow are these fossil fluctuations. And they've been mapped. I showed you examples of their mapping. This is just the most recent example by these 2 gentlemen, an Italian and a Frenchman, who pioneered the Planck satellite. So this is what they measured. But all the fuzzy stuff in the middle is just dirt from the galaxy, dust emission and other things. So when you have to clean the map, that's a long and laborious process, but when that's done, you end up with this beautiful map of the tiny differences in the temperature from place to place in the sky, few parts in a million actually. They're that sensitive. And so what you then do, how do you go from this to the curvature of space? Well, here is the great trick. What you do is you take what is called the power spectrum of these fluctuations. It doesn't really matter in detail what this is, but it's the angles at which you get most power, and there's a series of them if you do the Fourier transform of this map. But the point is that you notice there's one peak there. So this peak is something that represents a typical scale where most of the power in the fluctuations is. And if the universe were curved, you should see, slightly larger. If it were flat, it should be just that. If it were curved in the opposite way, it would, So by measuring the size of these fluctuations, you can compare it with your theory. And the amazing thing is that the conclusion is the universe is very, very big and it must be extremely flat, like that triangle on the left. So that's what we basically have learned from studying this. So let me sort of finish. This is the Big Bang as it once used to be. More or less what we see is what we get. There's a bit more out there maybe, but we'd have thought this, space is finite. It gets very complicated if it's not. But now we know on the contrary that the Big Bang, at the very least, we don't know if it's finite or infinite still, it's very, very big. And so this is our current picture of the universe. And it really gives you enormous pause for thought, because there are all these other galaxies out there, and just like our own, that we certainly can't see at the moment. Maybe in the future, as time goes on, we'll be able to see more and more, but it's going to take a very long time before we get to see things really far away. We are just, Copernicus said a long time ago that, he didn't like the idea of the Earth being in the center of the universe. He had the first heliocentric theory. We're not in a special spot. The universe is not going around us. We're going around the sun. And after that, even the sun has been displaced. The sun goes around the Milky Way, and now the galaxy is being displaced. And now all the galaxies we can see are just a tiny fraction of everything there is out there. So it should give us pause for thought as we move into things like Brexit and election season, all that stuff. And here's a wonderful quote from, again, 1669. Blaise Pascal: "Nature is an infinite sphere whose center is everywhere and whose circumference is nowhere." And that sort of encapsulates what we pretty much can see about the Big Bang. And here is a nice sort of summary, really, of where we are with modern cosmology. We look with these very powerful and very, very expensive telescopes. So we are in space or on the ground. We're talking, literally billions of pounds or euros or whatever to build these things, if not more, in the future. And we're looking through the Big Bang. And basically, as far as we've got, really, we're looking back. We're seeing structure develop. And on the left there, you see the greenish, yellowish stuff. That's the cosmic microwave background. That's this pattern of radiation where the fossils are imprinted. And at that point, as the universe expanded, it became transparent. And the radiation comes freely to us in the microwaves, and we can see it and map out those tiny fluctuations. In between then and now are what we call the dark ages. Before the first stars form, most of that space will be invisible between then and about halfway along. And then the stars form, we can map out the galaxies. And so the big challenge now with astronomy is to map out all the way back to the furthest things we can see. And then before then, maybe it's the turn of the particle physicists, the people who invented inflation and others, to tell us that really there was this period of immense inflation early on, and that what we're looking at when you make all this structure originates from the essence of the quantum theory, really, which seeds these fluctuations. And that's a story for the future, one that we really haven't, are just beginning to try to come to grips with. Anyway, it's a wonderful story, the expanding universe, and thank you.